So with us is Guy Glantser, who is going to present on working with very large tables like a pro in SQL 2019. I'm personally looking forward very much to this session. Go ahead, Guy.
Thank you, Daniel. So hello, everyone. My name is Guy Glantser. Let me introduce myself first. I'm a data platform MVP. I've been working with SQL Server for the past 25 years or so. I run a company. I'm the CEO and founder of Madeira Data Solutions. We are based in Israel, but we have customers worldwide. We provide services, solutions around the Microsoft data platform, not just SQL Server, but a lot of SQL Server stuff. And also, of course, Azure SQL Database, Managed Instance, and so on. You can find here my details. Please feel free to keep in touch, ask me anything. I would love to help if I can. And last thing I want to say, we have SQL Server Radio. It's a podcast that me and Eitan Blumin, my colleague, we release a show every month. And we talk about SQL Server stuff, anything around SQL Server, events in the community, new features, projects that we participated in. We interview guests once in a while. So if you're not familiar with it and you're interested in SQL Server stuff, feel free to subscribe. And so much about me. Now let's talk about the session. So I'm here to talk about how to work with very large tables, like a pro. This is important. And SQL Server 2019. Now, I must say that it says SQL Server 2019. I will talk about all kinds of features that were introduced in recent versions. Some of them were introduced in 17, 16, even 14. But not well, actually, I'm going to talk about partitioning, which is here since 2008. So we got a little bit of every version. And also everything that I'm going to show you here is also relevant to Azure SQL Database and, of course, Managed Instance. Azure SQL Database always has the latest build, so everything is already in there as well. There are some differences, of course, but as far as the things I'm going to show you here today, everything I show you here is also relevant for Azure SQL Database as well. So we are going to talk about first, what is a very large table? What is considered a very large table? Then we're going to talk about what it means to work with a very large table, what it means to work like a pro. I mean, everyone can work, but what are the results? Okay, what should you do like a pro in order to work with a very large table? And again, not specifically 2019, but I'm going to go through all kinds of new, relatively new features related to this. So let's talk about very large tables first. This is one table, and this is another one, okay? Is this a very large table? Probably not. Is this a very large table? I don't know. What is a very large table? Someone might say, okay, for me, more than 1 terabyte is, wow, this is really large. Someone else might say, hey, 1 terabyte is nothing. Okay, if it's not more than 20 terabytes, it's not a big deal. So it really depends, okay? And this is probably the answer to most questions. Of course, it depends. And for me, it depends on the how you take care of the table. So as soon as you need to take special care of the table, it's probably considered a large table. And for one person or in one environment, this can be as soon as it's 1 terabyte. For another person and maybe another environment with a different set of skills and tools, maybe 1 terabyte is not considered large table at all, but 20 terabyte is. So it really depends. As far as I'm concerned, it's not about the number. It's about what you need to do in order to work with a table. And we're going to talk about what it means to work with a table. But if you're used to work with tables in some way, I mean, taking backups, running queries against the table, maintaining indexes, and so on. If you're used to doing things in a certain way, and suddenly there is this table, which you need to do something else, it's probably considered a very large table for you, at least. Okay, so this is what I mean when I say a very large table. And when I talk about very large tables, specifically with the demo I'm going to use here, there are all kinds of tables with such names. Usually, it's either if you are in a data warehouse workload, it's going to be the FAC table. So it's a very large table with lots of inserts, which holds a history of many years or something like that. It might be also in an OLTP workload, and then it can be some kind of an audit or a log table like page views, transactions, events, things like that. What's common to all of these tables is that they all have a date and time column, some kind of a timestamp, and it's ever increasing. So usually it's only inserts, no updates. Sometimes you also have updates, but let's take the common case with only inserts, lots of inserts, ever increasing, and a very large table in terms of the number of rows. So for the sake of the demo today, I'm going to use a table called web page views. Let me switch to Meta Studio and show you I'm using a database. Of course, I will publish on my blog both the presentation and all the scripts I'm going to use here. I have lots of stuff to show you. So I'm going to send a link later. And we are using the very large table demo. And I have the page views table. Okay, so these are the common, very simple table. It has a date and time column. And if I just do select top 1000, this is how it looks like. Okay, I'm going to use this table for the entire demo. So it has an ID, identity, some URL, some reference code, which I'm going to use to join to another table to show some things, session ID, and the date and time, of course. Okay, very simple. Let's move on. What it means to work with a very large table. So I'm going to talk about four main areas. One of them is how you manage the table, and I will explain later what I mean by managing the table, how to query the table, and this basically means performance. I want good performance for my queries against this very large table. How to update the table, and I'm not just talking about the update statement, how to write into the table, insert, updates, delete, and so on. And how to maintain, how to do proper maintenance to the table, indexes, statistics, and so on. So these are the four areas I want to talk about and what it means to work with a very large table in this respect. So we'll begin with managing the table. So for managing a table, by managing, I mean how to control the storage, where the table is located, and things like archiving to make sure that we only keep the data that we need. Because in some cases, and I see it many times with customers, they have a very, very large table. And when I ask them, do you really need all of this data? They are not sure about it. And when we try to investigate and, oh, yeah, so we only need 3 years, but you have 15 years. So we can either archive or delete. And this can really improve stuff because you don't need to manage so much data. So this is one question, business question that you need to ask yourself. But let's talk about the technical stuff. So let me go to the demo. All right, so very large table demo. I want to talk first about partitioning. Okay, so this is the first thing. Probably for most so-called very large tables, you should use partitioning. It's important to say that partitioning, and this is kind of a common misconception. A lot of customers, a lot of users implement partitioning on very large tables because they want to improve query performance. And in many cases, they are then disappointed because I think in most cases, it doesn't really improve query performance. There are reasons for that. I'm not going to go into all the reasons, but in most cases, if you have good indexing, you have the right indexes, then just partitioning tables will not make a difference. In some cases, it even may make things worse. The big benefit of partitioning is the management of the table, is managing the table. It's things like archiving the table with a sliding window, and also maintenance, which I will talk about later. Only rebuilding the last partition index and things like that, instead of having to rebuild the entire table. Okay, so those are the main points. And let's see, I go relatively quickly because I think most people already familiar with partitioning. It's been here since 2008. If you do have any questions, feel free to ask questions in any of the channels, and Daniel here will help me with it. So I'm starting with looking at sys partitions. Currently, as you can see, the table is not partitioned. In SQL Server, even when a table is not partitioned, as far as the metadata, SQL Server always maintains a single partition, partition number 1 for the entire table. So it's kind of like partition in terms of the metadata, but it's not. Okay, so we have a single partition with 5 million rows, right? Yeah, in my example. Okay, so again, for the sake of our demo, 5 million rows is going to be considered a very large table. And I'm going to partition the table now. So first, we need to create a partition function. What I'm doing here, I'm doing a script, a dynamic script, because I want to create 182 partitions. I want to create daily partitions, and I want to keep only the last 6 months, only the last 180 days, 180 partitions. I also, and this is a matter of habit, there are all kinds of ways to do it. I usually prefer to add an extra partition for the entire history. So from the beginning of the data type until 6 months ago, which will always be empty. And also another extra partition for tomorrow, for the next day, for the next partition. Okay, so it's a total of 182 partitions. And I'm going to do it here using a select statement with dynamic batch. I'm not going to go into all the details now. You will have this script, of course. So after running this script, I'm going to have a partition function with 182 partitions. Then I need to create a partition scheme to map each partition to a file group. In many cases, we use a single file group, so I can simply say all to primary or all to whatever file group you want to use. Sometimes we also want to leverage different types of storage, so we can create multiple file groups and put each file group on a separate storage, and then we can play with it and put the hot data on fast storage, the cold data on slow storage. I'm not going to go into this, but this is also something you can play with. And then I need to take an existing table and convert it into a partition table. Now, if you are creating a new partition table, this is easy. We have a partition function, partition scheme. As soon as we create a table, we should create a table not on a specific file group, but rather on the partition scheme with the partitioning column. But now I have an existing table, a very large table, and I need to convert it into a partition table. There are several ways to do it. Some of them require some downtime, some of them not. If you don't want downtime, then, for example, one thing you can do, you can create another table, which is going to be empty with the exact same schema. It's going to be partitioned the way you want, but you're going then to switch the entire existing table as a single partition into the new table. And then you do the switch, you rename the table, and so on. So by that, you're doing it without any downtime, but you're not really going to split the existing data into daily partitions. You're going to have one big partition from the existing data, and from now on, you're going to start adding data in single partition. That's one option. If you want to split the current data into daily partition, then you need to move things around. One of the options is to simply rebuild the clustered index, which is what I'm doing here, okay? This is assuming you have a maintenance window, you can afford to do it. So this is also the primary key in our case. So I'm going to drop the primary key first. And then I'm going to add, again, the primary key as a clustered index. But this time, I'm going to put it on the partition scheme, and I'm going to specify the partitioning column, okay? And by the partition function, which I've already created, it's going to be daily partitions. Notice that in order to add a clustered index on a partition table, to make it a clustered partition, I also need to specify, since it's a primary key unique index, so I need a partitioning column. And I also, well, in this case, sorry, I want to create a primary key on the ID column. Okay, this is my intention. But since it's a unique clustered index, I also need to include the partitioning column inside the index. So it's not really behaving the same as I wanted to as far as the constraint. Okay, but this is a limitation. This is something, it must be part of the index, the partitioning column. So I have now a primary key on date and time and the actual primary key, which is the ID. So let's do this. And as soon as it finishes, we now have a partition table. Now I have here a very long query with lots of joins, with all kinds of catalog views, like sys partitions, sys indexes, partition functions, destination data spaces, and so on. And I have some filters to only filter on my specific table and my specific partition function and partition scheme, and only on the clustered index. And this will give me some interesting information about the table. So now, now you can see that we have 182 partitions in the table. As I told you, the first one will always be empty. Okay, we have the partition ID, the partition number, which is a running number starting at 1. We have the number of rows in each partition. We have the partition mean value, which is, in my case, it's daily partitions. It's always at midnight. Okay, so it's May 2nd, May 3rd at midnight, and so on. It's boundaries on left. Okay, which means if I get this specific value, it belongs to this partition and not to the previous partition. Okay, because it's part of May 3rd and no May 2nd, and everything is on the primary file. Okay, so this is the information I have here. So as you can see, the first one is 0, it's empty. And we also have another partition. So today we are in the middle of the day. So as you can see, we have the current partition of today is almost half of the number of rows. And we also have a partition for tomorrow. We already pre-allocated. Now, in order to manage the table, it can be the sliding window. It can be either to archive the table or to delete. Okay, in some cases, we don't really need more than 6 months. We can just delete the data. Sometimes we want to archive and move it to a separate table. So what I'm going to do, I'm going to create another table. I call it, in my case, it's to delete, just to make it more simple. And I have to use the exact same schema, the exact same columns, the data types, the exact same indexes in order to be able to leverage the switch partition statement. So this is going to be the other table. And in this case, the other table is going to be, since I only need to switch one partition each time and then delete it, that's my intention here, I don't need the other table, the toDelete table, to be partitioned. So it's on the primary file group. And then what I need to do, and this is something that I will do using some automation with a job that runs daily or something like that. First, I need to split the partition function. I need to add another partition for the next day. So each day I'm adding another partition. Another option, of course, is to pre-allocate partitions for the next 10 years or so, which is just metadata, so it's not a big deal. So you can do either or both. And this script will make sure that I have enough empty partitions for the future, for the first day. Okay, so this gives me the partition for tomorrow that I just created. And, sorry. A lot of copy paste here. Save script again. So now, as you can see, we have another empty partition for 2 days from now. And this is the main thing here. I'm running out of table, switch partition. I specify the partition number in the source table. And in this case, the entire table as the destination, because the destination table is not even partitioned. But I can do partition to partition, full table to partition, partition to full table, and so on. All the combinations are legit. So remember that I always have partition number 1 empty. So I start with partition number 2. This is the oldest one. Okay, and it's done. Okay, so it's just a metadata operation, no data movement. So it's very, very quick, no blocking, no nothing. And then in my case, I simply truncate the entire toDelete table, throwing away the oldest partition. Okay. We still have something left to do. Let me show you the state of the table now again. Okay, so now we emptied this partition. It's now also empty. Now we have 2 oldest partitions, which are 0. I'm going to merge them so that I always have a single oldest partition, which is 0. And this script will do the merge. All the scripts I show you here, of course, I can specifically put hard-coded values, but I want it to be dynamic so that you can put them in a job and it will run every day. So every day it will calculate the mean partition, and then it knows exactly what it needs to merge. Okay, so it will do the adjustments automatically. Did I run it or not? Let's see what happens now. Yes, I did. Okay, so we did the merge. Okay, and it's important that when you do the merge, like I did here, you have, in this case, 2 empty partitions. So again, there's no data movement. Otherwise, you're going to have data movement. It might take a lot of time and blocking and so on. All right, so we're done. There is a new feature starting with SQL Server 2016, which is the ability to truncate a specific partition. Okay, so it goes like this: truncate table with partitions, in this case 2. So it makes everything much more simple. I don't need to create a separate table and do the switch and everything. Simply truncate this partition, we're done. Of course, we still need to do the merge and so on, but this is only since SQL Server 2016. Okay, so now we're done with this. And let's run the merge code again, same code, copy paste again, and we're done. Okay, so this is the idea. So you put things in the right jobs with the right schedule, and everything is managed. This is the first thing I wanted to show you. So let's get back here. So the partitioning, okay. Partitioning facilitates the data archiving scenarios. This is the main, the common scenario that people use with partitioning. You can optionally spread partition over different storage tiers using different file groups, okay? It improves table maintenance. This is maybe one of the great benefits when you work with very large tables. When I talk about maintenance, I will talk about some benefits using partition tables. And again, this is not necessarily going to improve query performance. Sometimes it's even going to make things worse. There are specific cases where you might get better performance, but this is not the main reason, the main benefit of partitioning. Remember that. Another feature for table management is stretch database. And this is another new feature in SQL Server, starting with SQL Server 2016. And I'm not going to demo this here because this will take a lot of time and it's a bit more complex. I'm just going to go through the idea, okay? So if you want to explore more, go and read about it. There are some great demos in the Microsoft documentation. So the idea of stretch database or stretch table is that everything is done for you. If you have a very large table on-prem and it consumes a lot of storage, and of course, like most of cases, you have hot data, let's say it's the last month or the last year, and then there is cold data, which is most of the table, the last 10 years that you use rarely. It's a waste of resources to put all of this cold data on your local storage, which costs you a lot, and you need to expand it all the time, and so on and so on. So what you can do, you can stretch the table to the cloud, to Azure, and by just enabling this feature, you don't have to work too hard. It will create a database in the cloud, an Azure SQL database for you behind the scenes, and it will move transparently all the cold data based on your definition. You can say, okay, move the entire table, or here is the policy. Move only the data that is older than 1 year, for example. It will move it into the cloud transparently. It's completely transparent to the application. You don't have to change any of your code. You access the table as if everything is local. But as far as the storage, you only store the last year in your local storage. Of course, this means that when you query data from 5 years ago, you will have some latency. But this makes sense because you only do it rarely. Every time you query for the last year, it's going to be very fast because it uses your local storage. So this is the idea. It's transparent. It's quite easy to set up. Well, actually, it might look a bit complicated, but it's not that complicated. You need to first run the data migration assistant, okay, which is a tool you can download. And one of the things that this tool can do is to assess which tables are good candidates for stretch table. You need to enable remote data archive. That's how it's called in the instance level by using sp-configure before you can start using this feature. You need to choose either an existing Azure server if you already want to use a specific one you're already using, or create a new Azure server to host the Azure SQL database. You need to create a firewall to allow connection between your on-prem database and the Azure SQL database. It might sound complicated, but it's not. You create a database master key in order to encrypt the credentials you use to connect to the remote database. Then you create a database called credential to connect, which is encrypted by the master key. You need then to enable the same feature at the database level. You need to, optionally, you can create a filter function. And in most cases, you will because you only want to move the cold data less than a year ago and so on. But you can move everything. It will still be transparent. So it will feel like a local table, although everything is in the cloud. And then you need to enable this feature at the table level. Okay, so this is more or less the steps you need to take. Go ahead, explore, read about it, test it. There are some good use cases, again, depending on the size of the table, the storage you have, the cost you pay for it, and some other factors you need to take in there. So this was about the management of the table. Let me see the time. We're good. So let's talk about querying the table. Okay, let's talk about performance. And in this case, I want to focus on the ascending key problem, which is a very common problem in many workloads, in many databases. And the problem, let me simply demonstrate. This is the problem. And I want to include the actual execution plan. And I'm going to demonstrate the problem. So what I'm going to do now, I'm going to simulate. Okay, let's go 1 week back in time. Okay, so I'm going to delete data from the last week from the table. And then I'm going to update statistics for the table with a full scan. So they are very accurate, very up to date, but they are 1 week ago. Okay. It runs very fast because it's just a demo, right? It's not really a very large table. In your production, it's probably going to take longer. Now I'm going to insert data again into the table for the last week. Okay, so I'm going back into the present. But remember that I updated statistics 1 week ago. Now, a week of data is not enough for SQL Server to trigger automatic updates. And this is what I want to show you here. So now I have a query here that selects from my table. It also performs a join to another table based on the reference code. And I only filter for rows from the last week. Okay, and let's see what happens. So it gives me 192,000 rows. If you look at the execution plan, it performs a clustered index seek against my table. This is the actual number of rows, and this is the estimated number of rows. Oops, only 1. So based on this 1, SQL Server now generates a plan which is really poor for this query, it thinks it only gets one, so it does a nested loop. So it's going to do, it thinks it's going to do only one iteration of this clustered index seek, but in reality, it's going to do 200,000 clustered index seek operations. Okay, this is the problem in this case. And this is a very common problem. The problem is that SQL Server relies on statistics, and statistics were updated last week. And based on statistics, there is no data in the last week. Okay, nothing happens. It's because it's not updated yet, although we have 200,000 rows. Problem. Okay, so this is called the ascending key problem. Let me show you several approaches how to solve this problem. First of all, let me show you the statistics, the histogram. Okay, so as you can see, the last value in the histogram is last week, October 21st. Okay, and this is actually the problem. And I'm going to, okay, I didn't tell you before. I know that I told you I'm using SQL Server 2019, but I cheated. I used the compatibility level of SQL Server 2012 on purpose. Okay, so what I showed you now, it's how SQL Server behaved in SQL Server 2012. And if you're using SQL Server 2012 or even earlier than that, this is how it's going to behave. This is, you still have this problem. Starting with 2014, and with every version since, we have new features, new enhancements that partially solve this problem. So let's start with SQL Server 2014. Okay, I'm moving to 2014 now. And without changing anything, I'm now running the same query. Of course, it's the same results, but it's a different plan now. It's a completely different plan. If we look at this, then now it's still the same number of rows, but look at the number of estimated rows. Okay, so it's not one. It's still not accurate, but it's a lot better than saying just one. And it results with a better execution plan in this case. Now, where this comes from, we didn't change anything. Okay, so this comes from the new Cardinality Estimator. One of the big changes that Microsoft made in SQL Server 2014 is to rewrite the Cardinality Estimator, the component that is responsible for estimating the number of rows based on statistics. And one of the changes they made is specifically recognizing the ascending key problem. So the Cardinality Estimator identifies this pattern and it says, okay, I understand that this is an ever increasing column. I understand that it was last updated last week. I know that there are probably more rows in the last week. I just don't see them in the statistics. So I'm going to assume, I'm going to calculate and estimate more or less how many rows based on the pattern so far are going to be there in the last week. Okay, which is better than just saying nothing or one in this case. Okay, so this is one thing you can do, simply upgrade to the latest version or to at least SQL Server 2014, but it's still not good enough, right? So I want to show you some things you can do. One thing you can do, for example, if you are using the new version, but for some reason the new Cardinality Estimator performs worse than before, this can happen. What you can do is use phrase flag 9481 to instruct the optimizer to use the old version of the Cardinality Estimator for this specific query. And this is important because if you haven't done it yet, if you are going to upgrade from 2012 to a recent version, it's going to happen to you, trust me. For some queries, you're going to have a degradation in performance. It's going to be worse because of the new algorithm. It happens, and you need to identify those queries. And one of the first thing that you might want to do is use this phrase flag to first get the good execution plan back. Then you can sit down and optimize the query and see what you can do about it. Okay, so it's an important tool you need to be aware of. So now, even though we are in 2014, we are back in the previous plan with the estimation of 1. Okay, so in this case, it's not better, but let's see what happens when we go to 2016. Oh, and before this, sorry, something else. Before 2016, there was trace flag 2371, which you can enable on a server level, probably as a server startup property. And what it does before 2016, the algorithm, the threshold for SQL Server to update statistics automatically was 20%. So you need to wait until 20% of the number of rows in the table change before SQL Server triggers automatic update. For very large table, this might take a lot of time. Okay, so let's say you have, like we said, let's say you have 10 years of data and you insert data with the same rate, more or less. So for 20% out of 10 years of data, this means 2 years. You need to wait 2 years before the next update statistics. So this is crazy, right? We want to know how many rows are in the last week. We have to wait 2 years to get that information. It doesn't make sense. So you could enable trace flag 2371, and then it's not 20%, it's a dynamic percentage. As much as the table becomes larger, the percentage becomes lower. So it keeps more or less a better frequency of the automatic updates. Still not good enough in many cases, but better than nothing. Starting with 2016, this becomes the default. Okay, so as soon as you use the compatibility level of 130, now it's a default behavior. You don't need to enable this trace flag anymore. So this is another change. If I go now and run this query. Okay, so now look at this. We got a different estimation again. Okay, which is better. Still not accurate enough, but better than before. So now the reason is because we're using the new behavior. As soon as we upgraded and we ran this query, SQL Server said, okay, so now under the new threshold, I need to update statistics now. Okay, because inserting data into the last week, which is what I did before, under the new threshold is enough for triggering an update statistics. So it updated statistics and now has a better estimation. If we look at statistics now, you can see that we have a different histogram and it ends as of today, as of now. Okay, so it's now updated. Another option, of course, is simply update statistics yourself. And then we can also control the sampling rate. And I can say, okay, I want to be accurate. I can update statistics with a full scan. But the problem is that for a very large table, this will be very resource intensive operation. It can take a lot of time and resources. And if you are a 24/7 shop, it might be a problem. You don't have really a maintenance window in which you can allow yourself to run this statement. Maybe you can, this is great, but not always. But this is certainly an option. And now I have a full scan. So the row sample equals the number of rows in the table, and it's updated as of now. Let's move on. Now, by the way, if I run the query again, even though I just updated statistics with a full scan, you will see that we get, sorry, it's not what I wanted to show you. My bad. Okay, forget about it. So now I have a new statistics updated with a full scan. And as you can see, I have a much, much better estimation. It's almost the same as the actual number of rows. This is like identical for me. Okay, this is great. Okay, because we are using an updated statistics as of now with full scan. Okay. We can also use option recompile in some cases. Option recompile will compile my specific query at runtime every time. So what this does, since it's at runtime, it will take into account, it will evaluate, depending on the query, it will evaluate this expression better. It will trigger statistics update if it needs to. It recompile based on the new statistics that it has. And in many cases, it will yield better results, better execution plans. But be careful, it's really dangerous if you're going to use this with a query that is executed many, many times per second concurrently. It's going to bring the server to its knees. It's going to have to compile so many times. CPU will go to 100%. Be careful with it. On the other hand, if you have a data warehouse workload, for example, and only a certain amount of users are working concurrently and run reports once in a while, this might be a great thing to do, adding option recompile to your queries, because each and every time you're going to get the best possible execution plan for this specific execution. So be careful, but use it if you can. Okay, what else? Different cell. Okay, we talked about that. Let's move to SQL Server 2017 and see what happens. So in this case, let me show you the plan and the estimation. The plan looks the same. The estimation is the same. There's nothing new. A lot of things are new in 2017. There's nothing new in respect to what I'm showing you here. Okay, 2016 had a lot of new features related to statistics. 2014 as well. 2019, I will show you later. But in 2017, nothing special. Let's go to 2019, the latest version, and see what happens now. So in 2019, we have a different plan altogether. So it's not exactly related to statistics specifically, but if we are here already, let me show you one of the features. Actually, it started with 2017. It's called intelligent query processing. It's a family of features which really enhance performance potentially of execution plans. One of them, for example, is the adaptive join, which is a really cool feature. With the adaptive join, instead of deciding on the first execution whether to use nested loops or hash match, now SQL Server can say, okay, I have a plan with both options. And at runtime, in each execution, I'm going to take a decision which one is best. But it's pre-compiled. I know what to do already. I just need to take the decision, which is a great feature. And it really helps performance in many, many cases, especially with parameter sniffing issues. In 2019 specifically, we have now all of those features also work on row mode, on row store indexes. We have row mode and batch mode. So in 2019, we have batch mode execution. If you look here, you will see that the mode is batch, okay? So I didn't show you this before, but before it was only row mode. So now we have a batch mode execution, which is better in terms of performance and runtime. And also we have lots of features that currently also work with row mode. But in this case, it's batch mode anyway. So we get batch mode, we get adaptive join, we get features like memory grant feedback, and some other cool stuff, okay? Again, not related specifically to statistics, but good to know. All right, let's go back to 2012. Wow, history. Okay, so I want to show you something. If we go back to 2012, I want to simulate the problem again. Let's delete the last week. Let me update statistics with a full scan. And let me insert rows into the last week again. So we'll have the same estimation of one row, just like before, because we are using 2012 now. Let me show you the statistics, the histogram. Okay, so it's updated as of last week, October 21st. If we run the query again, just to make sure, we should get the same estimation of one row. Okay, so another way to solve this problem is to use filtered statistics. Filtered statistics is a very powerful tool. They have all kinds of use cases. I think they're underutilized in many cases. What you can do, for example, and in this case, you can do it in 2012, 2008. Filtered statistics have been here since 2008, actually. Yeah, filtered indexes were invented in 2008. So on any version, you can do this. What you can do, for example, you can create a filter statistics, in our case, statistics on the date and time column, but with a filter on the last week. Okay, so assuming our main use case, the hot data is the last week, I can create a filter statistics, a complete histogram only for the distribution of the data in the last week. And in this case, since it's a very small portion of the table, I can afford to do it with a full scan. It will happen instantly compared to doing it over 7 years or so. So let's do this. And I get an error. The reason I get an error is that in order to create a filter statistics, the filter definition must be deterministic. Okay, and this is not deterministic because I use sys_daytime. It changes all the time. Okay, I must use a deterministic expression. So what I will do, I will use a dynamic code. I will calculate here in the variable the last week date, and I will put it here inside a string, and then I can use a hard-coded string. Of course, this means you need to maintain the solution. So for example, you need to have a daily job that deletes the previous filter statistics and creates a new one for the now last week. Okay, so let's do this. But as you can see, it runs really, really fast. And now I have a complete histogram, a very detailed histogram, which is also very accurate because it uses full scan just for the last week. So I can get very, very accurate results by using this histogram. So now I'm going to run the same query again. Give me data from the last week. And as you can see, oops, didn't work. It didn't work. It still estimates 1 because in 2012, SQL Server can't use filtered statistics for such a query because you're using this expression here. It can't evaluate and say, okay, I know that the filter statistics, the data contained within the filter statistics is inclusive, contains everything that I need from here, okay? It doesn't have the ability to do it, so it will not use a filter statistics with such an expression. What a shame. Let's try something else, okay? I want to try a parameterized dynamic SQL, or it can be a store procedure, it's the same thing, okay? You use parameters. So I have now a parameter for the last week, okay, and I'm going to use SP execute SQL with this parameter. So let's see what happens with the parameter. Think about store procedure. This might be the common case. And again, we have the same problem. So when you use parameters, SQL Server will never use filter statistics because it needs to create a plan, put it in the plan cache, and then reuse the plan for different values. And maybe in a future execution of the same store procedure, someone will use a different value, which is not contained in the filter statistics. And now we're going to reuse a plan that is not, that doesn't match the new value. So SQL Server will never use filter statistics. Another option is to use a local variable, and then I'm going to put the local variable value, the constant value in here. So in this case, we're using a constant value. And now, as you can see, we get a much better plan. And look how much accurate it can get based on the filter statistics only for the last week. But the problem is we now need to rewrite our code. We can't use parameters. We can't use expressions, complex expressions. We can only use constants in order to leverage filter statistics. Not so good. But this is 2012. What can we do? I want to show you something. There is a trace flag 9204. And this one means just output the results to the client, to the screen. This gives me all kinds of trace flags. One of them, this one, gives me information about the statistics that the optimizer used during optimization. And I can see here that it used our filtered statistic. Okay, we have the information here. We can look at C stats and so on and verify that this is the statistics, but we only have a single filter statistic, so it's probably this one. Okay, so you can get this information for here to make sure that you understand how it works. It really used the filter statistics. And in this case, with the expression, I can prove to you, even though you already know that SQL Server didn't use the filter statistics because it's an expression. So we don't have the filtered stats loaded here. And this is SQL Server 2012. Let's go back to 2019, back to the future. In 2019, actually starting in 2016, this was the version when it changed. Now, as you can see, we get adaptive join, but we also get the great estimation that we saw before using the filter statistics, even though we used this expression. So in 2016, Microsoft said, well, you know what? Actually, we can use the filter statistics in the first execution and put the plan in cache, and we're okay with it. Okay, so maybe in the future, you're going to use a different value, but at least you have a plan. At least for the first execution, you had a good plan. And it's better in most cases than saying, I'm not going to use it at all. Okay, so this is great. And also, oh, by the way, I want to show you now that it uses the filter statistics. And if you look here, nothing. So this is a good demonstration of what an undocumented, unsupported trace flag means. Okay, so at some point, Microsoft stopped supporting this. It doesn't reproduce anything, so don't rely on those. There's other ways. I want to skip it, okay, because I don't have enough time. You have another trace flag which includes more information in the execution plan that you can use to troubleshoot exactly which statistics are used and some more. Let's go back to new features in 2016 and above. So now, again, this is the example with the parameter. So this is another thing. When you use parameters, SQL Server still can't use filtered indexes. It will never use filtered indexes because it needs to reuse the plan, but it can use filter statistics, as you can see, with parameters starting with SQL Server 2016, which is great. Okay, let's drop the filter statistics. And the last thing I want to show you is related to the ascending key problem. Let's simulate the problem again, delete data from the last week. Now I'm going to have the statistics with incremental equals on. This is another great feature which was added in SQL Server 2014, and it's related only to partition tables. And remember, our table is now partitioned. If you have a partition table, you can create incremental statistics like this, either by creating a new one or updating an existing one. And it's a little bit confusing because unlike partition indexes, you don't really have a statistics object for every partition. You still have a single statistics object, a single histogram for the entire table. But the calculation and the threshold of when to add the statistics are now calculated based on per partition basis. Okay, and this yields, in most cases, much better results. So let me show you that we still have a single histogram in this case. But now, if we try to insert that data into the last week, so what we're doing now, we have 7 empty partitions in last week. We're going to insert data into all of them. So for each one of them, we cross the threshold. So SQL Server is going to update the statistics for each one of those partitions and recalculate the entire histogram based on that. So we get a very accurate statistics after this insert is done. If we run this select again, then we get a very good estimation. Okay, so you can see 191 as opposed to 192. And now we still have a single statistics. We don't really see a statistic per partition, but it's updated as of now, and it's much more accurate. If we insert, let's insert additional data for like data for 3 hours, okay, from yesterday. I want to show you this amount of data is not, at least from my testing, is not enough to trigger an automatic update. So we're going to see the same estimated number of rows. Okay, just like before, 191. And we can also see here that it's the same exact time as before, wasn't updated. If we look at the partitions, then yesterday is this partition 178. Okay, so you can see it has more rows because I inserted more rows for yesterday. And what we can do is add the statistics manually for a specific partition. So if you have a case where something goes wrong with a specific partition, there is a bulk insert of some historical data for some reason into a specific partition, specific day, then you can manually update statistics only for that specific partition. Notice that you must specify with resample because it must has the same sampling rate as the entire table. Okay, so this is the only option you have, but you can very easily and very fast update a specific partition. And now it is updated with the information in the histogram. And if I run the same select statement, I should get a little bit better estimation. Okay, so now it's, where is it? 194. Okay, so it's closer to the actual value. And the last thing I want to show you, if you want to tell SQL Server, okay, whenever you automatically create statistics for a partition table, create them already as incremental statistics. This is how you do it. Okay, by default, it's not the way it works. It will create regular statistics. You can run this, and it will create automatically incremental statistics. So this was about performance, about querying the table, and about the ascending key problem. A fast recap: you can either update statistics manually, if you can afford it, once a day, once an hour, whatever. You can use the new Cardinality Estimator starting with SQL Server 2014, which identifies the ascending key problem. You can use trace flag 2371 if you are before 2016, or if you are 2016 onwards, this is the default behavior. You can leverage filter statistics, which are really powerful. And starting with 2016, you don't have to change your code. They support different expressions and also parameters. And you can use incremental statistics with partition tables, which I think should be the default way to go unless there is a reason not to do so. All right, next is data load. I hope I have enough time. So for the data load,
Can I just insert, do you want the attendee questions at the end, or do you want me to?
No, let's do it now. Let's do it. If you have any questions, let's do it now.
Right, because it pertains to filter statistics. Mikhail says, filter statistics is awesome. Are there any limitations as with filtered indexes?
Well, like I said, with filtered indexes, first of all, anytime you create a filtered index, it will also create a filter statistic behind the scene with the same filter definition. With filtered indexes, there are limitations. Like I said, if you have a store procedure, you have a parameter, and it matches the definition of the filter for the first execution with the first parameter value, SQL Server still can't use the filtered index because it needs to reuse the same plan for other values as well. It just can't afford to do it. So it will never use filtered indexes unless, by the way, if the filter definition is null or is not null, this is a specific case where SQL Server says, okay, I understand that you're not talking about nulls. I can use the filtered index. That's okay. Or you can add option recompile, for example. In this case, every time you're going to have a recompile, and then SQL Server can afford to use filtered indexes. Like I showed you with filter statistics, it's a different story. Well, if you are on 2012, or sorry, 2014 or earlier, it's the same story, more or less. Starting with 2016, for filtered statistics, SQL Server can still use filter statistics with all kinds of expressions and also with parameters. So this is good news. I hope this answers the question.
Yeah, thank you. So the question was asked before you elaborated on them. So
okay, great.
Thank you.
All right, let's move on. Let's talk about not update, but insert, which is the most the common scenario. We insert a lot of data into the table, and we want to make it faster. So let me show you, demonstrate the problem first. And I apologize, I'm going to run it a little bit quickly because I want to have enough time to show you everything that I want to show you. So in this case, what I do, I have, let's assume that this is my application. It gets data from somewhere, and it inserts the data row by row. Okay, so I begin a transaction, insert a single row into the table. Here is just some random data. And then I commit transaction, and I'm going to run it lots of times, okay, one after the other. So this would simulate my application. And if I do this, then if I look, okay, I'm not going to do it now. If you open Performance Monitor and you look at two specific counters, batch requests per second and log flushes per second, okay, so you see that some values, I will show you how to improve them later, but my intention is to improve this mainly. This is the throughput. I want to be able to make more batch requests per second in my server using the same amount of resources. And if we look here, what I'm going to do here, I'm going to clear the wait stats, and then I'm going to select from System OS wait stats with ignoring some wait types. And I want to show you that in this case, the biggest wait type is write log. Of course, this is all I'm doing, right? So in your production, you might see different things, but you see usually with such workloads, you'll see lots of write log waits, lots of waiting tasks, and the total wait time is high. And write log means whenever you need to flush the log buffer into the disk, into the transaction log file, you need to write into the LDF file. You have to wait until it finishes, and you wait with the write log, wait type. And this will slow things down because you need to wait until you get the commit, until you can release the logs. And there is a new feature in SQL Server starting with 2014. Yeah, 2014. So this is the write log wait type. There's a new feature called delayed durability. Delayed durability is not good for all cases. It can be dangerous because you might lose data. Okay, so for some cases like financial data, you really don't want to use it. But in many cases, if it's like an audit table, a log table, you can afford to lose some data once in a while. This can be a really great feature that can really improve the throughput. So let me show you. Okay, very quickly, let's talk about the properties of transactions. I'm talking about durability. Durability means whenever you do a commit transaction, you have to wait until the data is persistent in the log file before you can get an acknowledgement for your commit and release the logs. And this can take some time. Otherwise, you cannot promise that it will be durable. Now, if we look at the fully durable transaction, this is how it behaves by default. Okay, then we have a request. We have the buffer pool where we have data pages in cache, and we have the transaction log buffer. Every database have a single transaction log buffer. It's as far as I remember, it's 60K in size, 60 kilobytes. And what happens is, let's say we have a request, some update statement or insert statement, like our example. So the insert statement goes first to the buffer cache. We had to insert a row into the specific page, data page in cache. It also goes into the transaction log buffer. The audits, the statement itself, and all the information in transaction log is currently in cache. We still don't get a commit. If we want to commit a transaction, SQL Server first need to flush the content of the buffer into the LDF file, and this will be the write log wait type here. It takes a little bit time, and then we get a commit. Okay. Again, let's do it again. Write log wait. We need to flush. Then we get a commit. Third time, just to make sure you understand it. I'm kidding. And then at some point, asynchronously, we also have the checkpoint, which will take all the dirty pages and flush them into the data file. But this is a different story. Okay, this is the standard way. Now, if we want to enable delayed durability, this is how it works. Take a look. We run the request, we get a commit instantly. So even though the transaction log entry is still in the memory, it's not persistent yet, we might lose it. If something happens now to the server, we lost this. Even though we got a commit, we lost a transaction. During recovery, we will not have it anymore. And this is the risk, of course. We might lose data, but assuming that in most cases it doesn't happen and we can afford to lose data here and there, it can really improve the throughput because we don't have the write log anymore. Everything is much faster, okay? Commit, boom, and so on. And only when the transaction log buffer fills up, we are going, okay, sorry, this is a checkpoint. We are going to put all the content of the transaction log, multiple transactions, only a single round trip to the transaction log file. When is the log buffer flushed to disk? First of all, as long as you have a fully durable transaction in the database and it needs to commit, it uses the same single log buffer, it needs to flush the buffer. So if you want to leverage the power of delayed durability, but in the same database, you have different transactions running in fully durable way, you're not going to feel the difference. Okay, depending, of course, on the amount of transactions you're going to run. You can also do it manually. You can run this system stop procedure to flush the transactional buffer to disk. And also, if it fills up, of course, every time it fills up, you have to go to this. And in addition, Microsoft added every few milliseconds, just to make sure if it's an idle system, to make sure it doesn't stay in memory. It's not really relevant for real production system. You're not going to get so far. But just that you know it's there. You can control delay durability either at the database level. You have either disabled altogether or forced. All transactions in the database are going to be delayed durable. Or you can specify allowed, and then you can specify which transaction as part of the commit statement, if it's going to be delayed or not. You can also do it at the atomic block or the natively compiled procedure level for in-memory OLTP. Some transactions that are always fully durable. So if you have a transaction that performs against tables with either change tracking or change data capture, they will always be fully durable, regardless of what you tell them to do. Also, cross-database transactions will always be fully durable because of some limitations there. And for some features, transactions only as soon as they are made durable, they will be considered. So for transactional replication, for example, only after transaction is made durable, it will ship to the subscriber or to the distributor actually first. And same for log backups. Only when transaction is durable, it will be contained in the log backup. And of course, the same for log shipping because it uses log backup. So it's the same thing. The benefits, why should we use it? So we should use it because we have less round trips to the server, to the log file, less write log waits, shorter transactions, which translates also to less logs. Logs are released earlier, and the bottom line is better throughput, okay? So, and of course, remember that you might lose data, okay? So be careful with it, only for tables where you can afford it. And again, sorry about that. I'm not going to show you perf mode and how the graphs look like because I don't have enough time. You can test it yourself. But the idea here, let me just show you how to use it. Oh, sorry, I didn't stop it. Now we have lots of data in the table. Rollback transaction, okay, we're good. Now I can do this, alter database, set delay durability allowed. The default is disabled for backward compatibility. And now if I do the same thing, then what you will see in the graph in Perform, you see much higher throughput, batch requests per second. And if I clear the wait stats again, and I run this again, that now no write log at all. Okay, you don't see any write log. Something else now is at the top, ASIC network IO. Okay, so you might have some write log, but it's a lot less than with the regular transactions. So it's much better in terms of the wait statistics and in terms of the throughput. Of course, this is when I do a row by row. I have here a demo, which I'm going to skip. If I'm going to run this, let's say 1,000 rows at a time, okay? So depending on the size of transactions compared to the size of the log buffer, it might be not really impactful because let's say every 500 transactions, the buffer fills up and we have to go to disk anyway before the commit. So there's not much of a change. So it really depends on the amount of rows and the size of the transactions. All right, let's move forward. Remember to use delay durability to at least experiment with it for the right use cases. Yes, Daniel.
Quick question from Forrest McDaniel. This one's an interesting one. How does delay durability affect log hardening on a synchronous availability group replica?
Okay, good question. So again, for synchronous replica, the transaction will only go. I'm not 100% sure. I need to double check, but as far as I remember, it will go to the subscriber only as soon as it becomes durable. So it's the same.
It should be like replication, right?
Yeah, the same behavior as replication.
Yeah.
Okay, I need to double check that, but I'm pretty sure this is the way it works. Okay, thanks for the question. Let's move on. This is race against time. Okay, let's talk about maintenance because I have some important things to show you about maintenance. First, index rebuild. Before SQL Server 2014, what we could do, we could rebuild the entire table or partitions offline. We could rebuild all the partitions online. We have online index rebuild only with Enterprise Edition. We could also rebuild a specific partition offline. Only starting with SQL Server 2014, I don't know why, only from 2014, you can rebuild a specific partition online, okay? But of course, if you're using today, 2019, 17, or so on, you're good. So first, I want to show you how to rebuild a specific partition online. But another feature in 2014 is the ability to wait at low priority, which is relevant for rebuilding an index online and also for switching partitions. For these two specific commands, I want to demonstrate what it means. Oh, and of course, in SQL Server 2017, there is another few feature with the ability to pause and resume an online index rebuild. So you can say, okay, I want to stop here because I don't have enough time within the maintenance window. I don't want to roll back everything, so I will pause the index rebuild and I will continue tomorrow or something like that. Also, if there is an error, something went wrong, it doesn't mean it has to roll back everything. You can continue after you resolve the error, like this space, from the place where you stopped earlier. Okay, so this is a great feature for, again, maintaining very large tables and indexes. Let me go to the demo. This is a bit of a complex demo. I hope I get it right. Okay, so first we can rebuild the entire table, all partitions offline. Okay, like this. And I have here the object ID of my table is this. And I'm going to use it here. It's the same one. Yeah, the same one. Okay. What I'm doing here, I want to capture the index rebuild batch and then to look at the requests and the log. You know what? Forget it. I will tell you how it should work because I don't have enough time. But the idea between offline and online index rebuild, sorry about that. With an offline index rebuild, the entire index is blocked. You can't access the index. And of course, this means kind of a downtime. You don't have access to the table if you need to use this index. And for very large tables, this might take a very long time. If you're a 24/7 shop, this is a problem. If you're in standard edition, you might try to use only reorganize and live with that. If you are with enterprise edition, you can use online rebuild. With online, you have a short lock in the beginning, a short lock at the end, and in between, you can continue to use the table and the index. So this is the way to do it. Online equals on. It might take some more time and lots of resources, but at least it's not blocked. You can have concurrent activity against the index while it's running. We can also have, like I said, the ability to do it with resumable equals on and then pause and suspend the index. So I have it here. Okay, so I'm going to run this. Okay, so I'm going to rebuild everything. And then I'm going to say pause. Okay, so I pause the index and now I get this. It doesn't look so good, but this is expected. Okay, so I killed the session that is currently running the index rebuild, but I didn't roll back the operation. So if we look here, we can look at sys index resumable operations. So we see that we have a resumable operation. This is the statement, the index rebuild. This is the index itself. It is paused, start time, last post time, and so on and so on. How many page count were processed so far? What is the percent complete? So we have lots of useful information. And then we can say, okay, now I'm good to go. Let's continue. Let's resume the operation. Okay, so this is dead by now, but now this session is continuing the index rebuild until it's done. And it should be done any second now. Okay, so we're done with this. Let's continue here. Again, we can rebuild a specific index offline like this. Okay, so this is very fast because it's just a specific index. And starting with 2014, we can also rebuild a specific index online. So again, if you're on 2012, you can't do that, sorry. And now I want to talk about the wait at low priority. Okay, so the ability now is to tell SQL Server when you need to rebuild an index online, and this might be a long operation. I don't want it to block other operations. Okay, and I will show you what I mean by that. So this is the default behavior. You have a queue. Okay, we have the scheduler, which needs to run requests. We have a queue, a runnable queue behind the scheduler, all the things that can run and are waiting for the scheduler. So let's say we have an insert statement. Okay, the insert statement goes into the runnable queue. The scheduler is free, so it goes into the scheduler and runs the insert statement. While it's running, we have an online index rebuild request going into the normal queue, the only queue we have. Now it's waiting behind the insert. Let's say that now there is another insert statement. It will wait behind the online index rebuild. So now this insert statement might be blocked for some time. As soon as this insert is done, the online index rebuild starting to work. And of course, now the insert can continue because it's online. Okay, so they can work at the same time, but it had to wait until the online index will start, and then it can finish. This one can finish, and we're done. Now we have the ability to wait at low priority for the index rebuild. So the way it works is like this. First insert goes into the scheduler. Online index rebuild goes into a separate queue, a low priority queue. So now the second insert can go into the same queue. It's the first one. It can start executing already. Okay. And as soon as both of them are done, now the online index rebuild can start, but it will wait. So this is wait at low priority. There are 3 options when you specify wait at low priority. There are 3 options you can specify for. First, you need to specify how much time to wait at low priority, at the low priority queue. And then you should specify, okay, after this time is done, what should I do? There are 3 options. One of them is, it's called abort after wait. So the first option is known, okay? This means simply do nothing, continue to wait at the regular priority, move to the regular queue and continue to wait there as regular. The second option is abort myself. So let's say in this case, I wait for 1 minute. If after 1 minute I still can't start running because lots of things happen and I wait all the time at low priority, I give up. I will not do it. Okay, let's try some other time. Okay, this is self. And also we can say abort blockers. So I really need to run this online index rebuild. I can wait for 5 minutes, but after that, sorry, I'm going to kill everyone and I'm going to run the online index rebuild. So let me try to demonstrate this. Where are we? Here. Okay. So first, let me demonstrate the first thing. Okay. Let me see that I get it right. So we have session 1 and then session 2. I hope I do it right. This is session 1. Okay. So session 1 is going to begin a transaction and it's going to do an insert without commit yet. Okay. Then right after that, and sorry, and I'm going to also run, I have here a script to show you what's happening now. Okay, so currently we don't have any waiting tasks. Nobody's blocking nobody. We only have a single insert that is running, has been running already. Now we go to the online index rebuild, but without waiting at low priority. Okay, so when we run this, it now needs to wait. So yes, I know it's online, but for the online index rebuild, it needs to acquire a lock in order to start. And currently the insert is blocking the table, so it can't start. Okay, it waits at regular priority. If we go here, so now we see that we have this session. This is the online index rebuild waiting for a shared lock. It needs to acquire a shared lock, but it can't. So it waits. Okay, and then we have session number 2. Session number 2 is also doing a begin transaction and an insert. And here's the problem. Session number 2 now has to wait. It waits behind the online index rebuild, even though it can run. Nothing is stopping it to run, but it waits behind the other one. Okay, so we might have lots of other requests now waiting behind this index online rebuild, and it's stopping all the rest from executing. This is the idea. Okay, this is what I want to demonstrate. As soon as the first, where is the first? Here it is. The first insert statement commits. Then now, first of all, the index rebuild. Oh, sorry. Okay, this is interesting. Now the second insert can run, okay? And the online index rebuild still needs to wait because it needs the shared lock. Okay, so now we also need to commit this one. And only now the index rebuild is done. Okay, so this is without waiting at low priority. I'm going to do this one more time with the wait at low priority. So session 1 first, like this, insert, then we do the, okay, let's choose just one of them. I'm not going to demonstrate all of them, all of the 3. So let's say I want to do this, the first one. So I wait for 1 minute at low priority, and then I move to the regular priority after that and continue to wait there. Okay. So if we look now here, notice that we have a new wait type. It's the same shared lock, but at low priority. So we have a separate wait type for each one of the for the locks that we need to take. So we now wait at low priority, just like before, but it's the other queue. We will wait for 1 minute. Okay, in the meantime, session number 2, and this is the nice thing here, session number 2, begin transaction, insert, it doesn't have to wait. Okay, that's the difference. Everything else can continue to run while the other one is waiting at low priority. If at some point there is no lock on the table, the online index rebuild can start. Otherwise, it will continue to wait for a minute. And after a minute, okay, so now notice that the online index rebuild is waiting behind 2 sessions. Okay, it needs now to wait for both inserts to release their locks, and it's at low priority. And at some point, after a minute, okay, a minute is gone, it moved to the regular queue with a regular wait type and continue to wait there. Okay, so of course now, as soon as we release the 2 locks, the 2 transactions, commit here and commit here, only now this can complete and we have no more locks, everybody's happy. Okay, and of course the same idea, I will not demonstrate it. We can do it with either killing myself or killing all others in order to start running the index online rebuild. So, a summary, time for a summary. I'm good with time, yay! We talked about working with very large tables like a pro in SQL Server 2019. We also saw some other things. And again, all of this is relevant for Azure Physical Database and managed instances as well. So we talked about what is a very large table. And of course, the answer is it depends. It depends on your specific environment, on your skills and knowledge and the set of tools that you are using. But you need to be able to recognize when you need to do things differently. And then you need to leverage the tools and features that we talked about here. Okay. So again, the definition, as far as I'm curious, is one that a table that requires a special care. What it means to work with a very large table, we talked about 4 areas: managing the table, partitioning, archiving, sliding window, and so on. Querying the table, the ascending key problem, lots of options there. Updating the table, or in our case, inserting into the table with high batch requests per second, using delayed durability might be a good option there. And maintaining the table, only updating indexes online, waiting at low priority, pausing and suspending and resuming indexes as we go, and things like that. Also, I didn't mention it, but I talked about it earlier, one of the greatest benefits of partitioning is to leverage the maintenance. Okay, so again, if you have a very, very large table of 10 years of data, nothing changes in the table for 10 years ago. There is no reason to update, to rebuild the entire index for all the 10 years, and also update statistics for 10 years because it doesn't change. As soon as you have a partition table, now you can only rebuild the latest partition, or maybe the last 5 partitions or whatever. And the same for statistics. If you leverage incremental statistics, you can only update the latest partitions. All the maintenance becomes a lot more easier. This is very important. What it means to work like a pro. So we talked about several things regarding managing the table. We talked about partitioning and also stretching the table to the cloud. Regarding the ascending key problem, just reminding you of all the options we use there. And again, you have the demo script, you can test it yourself and play with it. Regarding the write log problem, we can use delayed durability, and we talked about the benefits of that. And in order to solve the index rebuild problem, we can either rebuild a specific partition online, which is something we couldn't do before. We can use resumable online index rebuild and also wait at low priority. And as far as features, again, not just 2019, we talked about stretch database, new Cardinality Estimator starting with 2014, incremental statistics, delayed durability, and some online indexing enhancements. Some other things you might want to explore, which I didn't talk about: compress the data, use data compression. If you have a very large table, depending on the data types and distribution of values, you might get a really good compression ratio. This will not only reduce the storage space, but also improve I/O and improves performance, because you need to read less pages to accommodate the same number of rows. Optimize parallelism. When you query a large table, if you do large scans, parallelism can really help. And there are some ways you can optimize parallelism. This is really beyond the scope of this session, but you can do some tweaking, some things in order to improve the way SQL Server run parallel plans and optimize them even better. You can, maybe if this is the right case for you, you can use lower isolation levels. You can use read uncommitted, and for some, or with no lock. This is risky, I know, it has implications. For some cases, it might be a good solution, a viable solution. You also might want to consider read committed snapshot. This means you're going to have row versioning. You're going to have lots of overhead on TempDB. On the other hand, you don't have to wait for anything. You can have better concurrency. So there is a trade-off, and you need to test and see if this is a good choice for you. Column store indexes. If it's a fact table in a data warehouse using a star schema, this is a classic scenario for column store indexes. And column store indexes were first released in 2012, but with lots of limitations. They've been improved since then. Today, with the recent versions, this is a really, really powerful tool. So check, if you're not doing it today, if you have a data warehouse, you should really experiment and check out column store indexes. You can also use column store indexes alongside row store indexes in the same table at the same time. They will work concurrently. So there are lots of use cases for that. And the last thing I showed you earlier is intelligent query processing, things like adaptive joins, memory grant feedback. There are some cool features in 2019, like T-SQL function inlining, really great features for performance. So you should read about them, experiment, and see how you can leverage them with your workload. Thank you very much. If there are any questions, this would be a great time.
Thank you. I loved this session. It was high-paced. I could feel the entirety of the internet scribbling furiously and taking notes. That's the kind of session, and it keeps you very engaged. So I loved it. The only question since the last one was about the slide deck, and I suppose that's on your blog, right?
Yeah. So probably until tomorrow, I'll publish the slide deck and all the scripts as well in my blog. And I'll send you the link and you'll make it available, I guess, wherever.
And cool. And Manikan says, excellent demo. I like it. I can only agree.
Thank you very much.
Personally, I have been performance tuning for like 15 years and I had no idea about filtered statistics. I've been using filtered indexes forever, but filtered statistics, I was like, what?
Like I said, it's underutilized. I think it's really underutilized. A lot of people are not familiar with that, and it has really great use cases.
Mm-hmm. And I've used delayed durability for a number of times where I have ETL loads for data warehouses, where you can basically just truncate and reload, so it doesn't matter if it blows up. But I couldn't modify the source application to do bulk inserts. It would do a row by row insert, and it was unbelievably slow. So I set the database to forced delayed durability, and it went almost twice as fast. It was just amazing.
This is actually the classic use case. You have an ETL, and you have to use it row by row because you don't have a choice. This can really help you there. Absolutely.
Mm-hmm. So again, thank you so much for speaking at GroupBy, and we're just honored to have great speakers like we had all day yesterday and today.